Welcome to lecture 5 of week 6 of machine learning foundations. Today we'll continue the discussion about principal component analysis which we started 2 lectures ago. In the last 2 lectures we saw that PCA is an algorithm that can be viewed as minimizing the reconstruction error while doing dimensionality reduction for a given data set. In this lecture we'll take a totally different viewpoint where the goal is to maximize the variance of the given data set using projections. So we'll see that the same algorithm, which is the PCA algorithm, ends up achieving this objective as well, which is it maximizes the variance of the given data. And we'll also illustrate this by revisiting the example that we had before in the previous lecture. We'll revisit that example and see how the same algorithm is also maximizing the variance. Okay. Now we'll move on to the other perspective, which is PCA as maximizing variance. So let's start with something very simple here. Consider, so we've done projections before. If you go back to that notes, this segment will be, if you brush up that notes, this segment will be a lot more accessible. Projection onto a line given by a unit vector u1. Okay. Now let me just call this u, just for simplicity. Now for a data point xi, the projection onto line along u is xi transpose u times u. Now with the notation as before, if you have data, recall if you have a data set like this, data set d equals x1 until xn, xi belongs to rd. Now x bar is the mean x bar is 1 by n summation tan xi. Now given this, so just recall, so xi's projection is xi transpose u into u. The mean for this is this is a non-standard term, mean projected value, whatever it means. X bar transpose u into u. Now given this, the variance is given by how much this point goes away from the mean. Okay, this is the variance. Now summing the variance over all points, we obtain 1 by n, and of course averaging it, xi transpose u minus x bar transpose u square. Now this is the quantity of interest. Now we want to maximize the variance. I need to write equals 1 to n. And the goal is to maximize this over u. So that's really the PCA second interpretation. Now just notice that you want to maximize the variance of data, so 1 by n summation xi minus x bar transpose u square I equals 1 to n can be written just by following logic as in the previous lecture. Can be written as 1 by n summation I equals 1 to n u transpose xi minus x bar into xi minus x bar transpose u. And this is nothing but this is equal to u transpose cu, where c is as before. C is just 1 by n summation into n xi minus x bar into xi minus x bar transpose. So you see that even when you are trying to maximize the variance, you get the same matrix. Now what you do with this? Now you are just trying to find the projection onto a one-dimensional space. So you want to maximize. So the goal is to maximize over u transpose cu such that u transpose u is 1. Now using Lagrangian as before, it can be argued that the maximizer of u transpose cu is an eigenvector of C corresponding to the largest eigenvalue of C. Now this, of course, you can write down the Lagrangian and do the derivative and argue this. Okay. A calculus argument for those who are somewhat uncomfortable with the Lagrangian argument. I'm just going to show the same thing can be done using basic calculus. So what you want to do is you want to maximum your u transpose cu such that u transpose u equals 1, or equivalently what we will do is maximum over u cu by u transpose u. Let's maximize this. Now for notation, let any u be a vector with coordinates ut. Given this, you have a ratio, you are trying to maximize this, so let's calculate the partial derivatives. So dou by dou with respect to the ith coordinate of u transpose u is nothing but dou by dou u of I of u1 square plus blah 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 ut square. Okay, this is nothing but 2 times the ith coordinate of u. Now we will differentiate the numerator. This is nothing but dou by dou u of summation of I equals 1 to t, j equals 1 to t of say Cij Ui Uj. Just recall, don't get confused. This is ijth entry of matrix C. This is ith coordinate for the entry of U, and this is the jth coordinate of vector U. So given this, when you differentiate this, what you would get is 2 times summation of j Cij U j. This is nothing but I do this 2 times, take the ith entry. So now we come to the main thing. So you want to maximize this ratio. So use the quotient rule. So dou by dou ui of u transpose cu by u transpose u is nothing but u transpose u into the derivative of the numerator minus u transpose cu to 2 times ui. You want to equate this to 0. Let me call this star. Now star in vector form, star is equivalent to u transpose u, I'll get rid of the 2, into cu equals u transpose cu into u, or equivalently cu equals u transpose cu divided by 0 into u, or cu equals lambda u. So the maximizer of u transpose cu divided by u transpose u is an eigenvector of C. Now and max of u transpose cu divided by u transpose u is equal to lambda and eigenvalue of C. And if you want to maximize this, to maximize transpose cu divided by u transpose u, choose lambda to be the largest eigenvalue of C, and let u be the corresponding eigenvector. So that's really the point of this maximizing variance. Now we can extend this logic. The logic can be extended to the case when you have PCA parameter m greater than or equal to 1. So for instance, in the 2D case, we need u1 comma u2 such that both are unit vectors, orthogonal, and projected variance is maximized. What is projected variance? Projected variance is just, instead of u transpose cu, you would have two terms. You're just not projecting onto a line, but projecting onto more than a line, projecting onto a two-dimensional space. I'm going to skip the details, but it suffices to say that it can be shown that picking the eigenvectors corresponding to the top two eigenvalues would maximize projected variance, and so on. You can extend this so on. So in general, from a projected, from a maximizing variance point of view, what you do is, again, general from maximizing variance viewpoint, PCA, okay, in general from a maximizing PCA can be performed, PCA does pick top m eigenvalues of the matrix C with corresponding eigenvectors here is where the nomenclature comes. So UI are the principal directions, and whatever you project is the principal component. The projected values would be the principal components. So much for the projected variance. Yeah. Revisiting the example, you see the data is -1, -1, 0, 0, 1, 1. This is the data. And the projections will be the same as this. We just worked this out earlier, 0, 0, 1, 1. So just recall, this is x1, x2, x3. This is x1 tilde, x2 tilde, x3 tilde. Now, what is x1 transpose u1 turns out to be the square root 2 -1 -1 into -1 -1, not 1 -1, u1 is 1 1. Yeah, recall from earlier calculation that u1 turned out to be 1 by square root 2 1 1. So we're trying to project onto a space spanned by u1, and this is minus square root 2 x2 transpose u1 equals 0, and x3 transpose u1 is 1 by square root 2 1 1 into 1 1. This is square root 2. So projected variance is the average 1 by 3 into summation of the squares of each of this. Okay. If you go up here, go to this equation that I had written before maximizing. So projected variance is 1 by n summation xi transpose u minus x bar transpose u square. But x bar is just 0. So I'm just doing xi transpose u square. So 1 transpose u square plus x2 transpose u square u1 plus x3 transpose u1 square, which is nothing but 4 by 3. But this solution can be arrived at more directly. Question is how? Recall eigenvalues of CR 4 by 3 and 0, and from the passage before, if you go above here, then all you are doing is maximizing u transpose u such that u transpose u equals 1. Okay. And this so max over u 1 u transpose 1 transpose c u1 such that u1 transpose u1 equals 1 is achieved by, you know, u1 equals whatever u1 corresponding to eigenvalue 4 by 3, which is equivalent to saying equivalently the projected variance along a single line is just the largest eigenvalue is equal to lambda 1 equals 4 by 3. So think about this. Okay, so go back to the derivation, you'll understand that it's just the principal, the largest eigenvalue that comes into play. Okay, here is a summary of today's lecture. What did we learn today? We understood that PCA is an algorithm which achieves two objectives, which is it minimizes the reconstruction error, which was seen in the last two lectures, and it also maximizes the variance of the given data, which is something that we showed today. And we actually use these ideas of maximizing variance. We illustrated these ideas through the same example that we had seen before for minimizing the reconstruction error. And we saw that effectively when you are trying to maximize the variance for a given low dimensional subspace say of dimension m, given this input parameter m, all you have to do is you have to construct a certain matrix, a symmetric matrix, a real symmetric matrix using the data, and then pick its top m eigenvalues, pick the corresponding eigenvectors and use this to do projection, and what you end up in the end would maximize the variance, and alternately it would also minimize the reconstruction error, because it's the same algorithm that we arrive at while we are doing reconstruction, minimizing the reconstruction error as well as maximizing variance. We are arriving at the same algorithm, which is the well-known PCA algorithm for dimensionality reduction. Just that both viewpoints are valid. You could approach PCA from both viewpoints, and both are important viewpoints, and we could see both of these in actions in the context of a very simple example.